Hello, everyone. Thank you for coming. I'm Yuxing, and I will tell you about our paper, Transformers Implement Functional Gradient Descent to Learn Nonlinear Functions in Context. In-context learning is a well-known phenomenon in which the transformer can answer a query based on several provided examples. In our paper, we consider a mathematical abstraction where the transformer needs to learn a function based on a few provided demonstrations. Instead of words, the queries are d-dimensional vectors in Euclidean space. The prediction targets are scalar labels, which are some function f of x marked out in blue. We illustrate this pictorially at the bottom. For simplicity, the input dimensions is 1, so all the xi's are scalars. We are provided a sequence of xy pairs, which are the black dots, and they demonstrate some functional relationship. The transformer needs to infer this functional relationship to make a prediction for xn plus 1 marked out in red. Note that for each batch of inputs, the underlying function can change. In this paper, we will consider a simplified transformer model, which is obtained by sequentially stacking attention layers. We reserve the orange letter H to denote a nonlinear activation in the attention module. In practice, H is usually chosen to be softmax. Another popular choice of H is ReLU. Finally, we also consider the exponential activation, which is just softmax without normalization. The central message of our paper is that the transformer with nonlinear attention activation H implements gradient descent in function space. This is what enables the transformer to learn nonlinear functions in context. Specifically, each attention layer implements one step of functional gradient descent. Each different choice of H gives rise to a different function space, and therefore a different gradient descent algorithm. The right choice of H can significantly improve transformer accuracy. So, what exactly does it mean to implement a gradient descent? On the left here, I show a L-layer transformer. The input to the transformer is a matrix of n demonstration xy pairs and a query xn plus 1. The goal is to predict yn plus 1. At each layer I, we can read out a prediction for yn plus 1. We will train the transformer by minimizing the error between the last layer's prediction and the true label. Let us entirely forget about transformers for a moment and ask ourselves the question, how do we predict yn plus 1 given n demonstrations? Here is a very intuitive two-step procedure. First, we look at the demonstration points and find the best fit function from some class of functions. Second, we use the best fit function to predict yn plus 1. Concretely, the best fit function can be found by minimizing the empirical loss summed over the demonstrations x1, x2 to xn. Even more concretely, to find the minimizer of empirical loss, we can run gradient descent. And given enough steps, we will converge close to the minimizer. We show that when H is a kernel, there is a stationary point of the training object at which the transformer implements functional gradient descent with respect to the RKHS metric induced by H. To be clear, number R here denotes the functional gradient of R with respect to the RKHS metric. It gives the steepest descent direction of the empirical loss R, which is also the update direction for the gradient descent sequence. More precisely, The transformer's prediction at every layer is the same as making a prediction with that many steps of functional gradient descent. Thus, the prediction after one transformer layer is the same as using f1 of xn plus 1 to predict yn plus 1. The prediction of layer 2 is the same as using f2 to predict yn plus 1. And so on for every layer. Before moving on, let me briefly mention that in our experiments, the proposed stationary points seem to be consistently learned in practice. On this slide, I show 3 plots. The x-axis denotes training iteration numbers, and the y-axis is roughly speaking the log of the difference between the attention weights of that layer and our proposed weights which implement functional gradient descent. In this example, we train a 3-layer transformer, so there are 3 lines on each plot, 1 line for each attention layer. Each plot corresponds to a different choice of nonlinear activation function. As we can see, it appears that the transformer is consistently convergent to those stationary points during training. We can also show that choosing the right activation function to match the data distribution can be statistically optimal. Let cursive k denote a kernel and assume that the yi's are jointly distributed according to a Gaussian process generated by the kernel k. Furthermore, if the nonlinear activation h and the data generation function k correspond to the same kernel, then the transformer's prediction is statistically optimal in the limit of number of layers going to infinity. I now present a set of experiments which verify the statistical optimality of transformers when activation matches data. Each plot on this slide corresponds to a different choice of data kernel k. Each plot shows 4 colored lines corresponding to the loss value of 4 kinds of transformers with 4 different types of attention activation. The y value corresponds to the loss after training converges. The x-axis represents number of demonstrations, and in general, you do expect the loss to decrease with increasing contact length. The key takeaway here is that the best loss is achieved when transformer architecture matches the data. In the first plot, the linear activated transformer represented by the green line performs best for k-linear data. In the second plot, the ReLU activated transformer in blue performs best for k-ReLU data. And in the third plot, the EXP and the softmax activated transformers perform the best for k-EXP data. It may be a bit of strange that softmax beats EXP when data is generated from k-EXP, because our theory predicts that EXP-activated transformer should be optimal for k-EXP data. On the left, we show an additional plot of loss against a number of layers, holding the contact length fixed at 14. Note that this plot differs the right plot, where the contact length varies and the number of layers is held constant at 3. Here we see that as number of layers increases, the gap between EXP and the softmax is becoming to 0. This is consistent with our theoretical result, which guarantees statistical optimality of EXP-activated transformer as number of layers goes to infinity. In the bottom left plot, we repeat the top left experiment but use a smaller contact length of 6. Here, we see that the EXP-activated transformer significantly outperforms the softmax-activated transformer. Towards the end, I will discuss a final experiment involving multi-headed attention. The high-level takeaway is that by using parallel attention heads with diverse activations, the transformer can act optimally for a wide range of data distributions. For simplicity, our experiment will consider a two-headed transformer where one head is linear and one head had an EXP activation. On this slide, we show 3 plots. Each plot corresponds to a different choice of data distribution. The leftmost plot has data from K-linear. The middle plot has data from KEXP. The rightmost plot has data from K-diamond, which is the composition kernel by summing K-linear and the KEXP. On each plot, we show the laws of 3 different architectures. The one had linear activation in green, the one had EXP activation in yellow, and the 2 had activations in blue. In the first 2 plots, we see that the 2-head transformer performs as well as the single-head transformer that matches the data distribution. In the last plot, the 2-head transformer outperforms both the 1-head transformers on the K-diamond distribution. In summary, we show that transformers can implement functional gradient descent on the RKHS determined by its attention activation function. This enables the transformer to learn nonlinear functions in context. Furthermore, we show that choosing the right activation function enables the transformer to perform gradient descent on the right RKHS and thus obtain statistically optimal loss. In addition, we analyze certain stationary points of the transformer and show that they coincide with the gradient descent construction above. Finally, we observe empirically that the transformer seems to constantly learn to implement functional gradient descent during all our experiments. That's all. Thank you for listening.